Hi, this is Dr. Liu. In this video, we'll discuss how to add, subtract, multiply, and divide numbers with precision. So let's try to make solid examples of these very abstract concepts. So with precision, it just means how many sig figs should you get for your final answer. So let's think about something we can actually do in terms of add and subtract. So let's add. Okay, so in one experiment we're going to do in the intro labs is a projectile lab. So in this projectile lab, let's draw a diagram. We have a tabletop, and then this is just floor space, and we mount the projectile launcher. This launcher points upward at an angle, and it launches a ball. The ball lands here. All right. So our goal is to estimate or predict where it's going to land, but part of the lab is just to measure the distance of each landing. So we're going to start from this point where the ball leaves the projectile launcher, and we'll make a measurement. But this measurement is usually more than what we are equipped with a single 2-meter stick with. So say we have this 2-meter stick here. Here's a 2-meter stick, and it just doesn't reach that far. We can launch and land over 3 meters away. So we'll add another 2-meter stick. Try to put them next to each other, and we have another 2-meter stick. Right. So we're just going to make two readouts, and one of them is easy. This is a 2-meter, and that's still a measurement, that's still a readout. And then another readout is what about this, how many meters here, and then we add the two quantities together. So we can call this an L1, this is an L2, so two readouts, and L1 is 2.000, that is the millimeter range, 2 meters. And L2 is, let's make up something, 1.315 meters. So that's also the millimeter right here. Okay, so our goal is to add these two numbers together, right? So this basically comes with precision consideration. Say, for example, you were using two identical meter sticks, so that means they can measure as precisely as the other, so they can both supply millimeters of accuracy. So when we're adding, here's how we're doing it. So 2.000 adding with 1.315. So first we just calculate the numerical value, right? So here we have a 5, 1, 3, decimal, and 3. Okay, so then we should evaluate whether we have kept enough precision or not. So how do we decide? Well, first we look at the numbers, 3 sig figs after the decimal, 3 sig figs after the decimal. So 3 and 3. And as you may know already, that the decimal is not always a dot. In other parts of the country, the world, such as Europe, this could be a decimal comma, and thousands will be separated by dots. So I want to only say a decimal. All right, so we have 3 sig figs after the decimal. So after we add, we still should have 3. So what if we didn't do it this way? We had a 2-meter stick, but then we had another measurement device which is not very accurate, or maybe we didn't really do a very accurate readout. We're only able to read out down to the centimeters. Say we had 2.000 and 1.32 instead, right? Okay, so we just read 132. Here's a 0, a 2, 3, decimal, and 3. Okay, so now we have 3 sig figs after decimal, and we have only 2 after decimal. So should we keep 2 or 3? Well, let's think about this. You have a more precise measurement and you added, or rather you ruined it with a less accurate measurement. So the outcome is you can only tell as much as a 1/100th of a meter now, because you mixed a more precise number with a less precise number. So just think about that, right? So we're looking for 2, or rather the minimum, right? So the minimum of 2 and 3, which are these 2 digits after decimal, 3 digits after decimal. So that gives you a 2. So whenever you're adding, you first need to line up the decimal places, right? That's by default. And then look at how many sig figs each number has after the decimal places, and then decide to only keep minimum amount after the addition or subtraction is done. So now we should only keep 2. So this is 3.32. So if this is not a simple 0, then we need to round, right? We discussed that in the previous video. So now we have 3.32. And let's add the meters to the end in parentheses to indicate we have that, right? So this is basically how to add or subtract with sig figs. This is because we actually have such need to add or subtract. So what about multiplying, dividing? Okay, so in a different experiment, for example, we're just trying to find out the area of a table. Let's say projectile. This is our example. This is area of a table. Okay, so I know how to do that. So I got a table right here. I want to draw very accurate. Just kind of a cartoonized table. Alright, so we have a table here, and we're going to take 2 measurements. This dimension, let's call it x. So this dimension, let's call it x. And then we also want to take this dimension, which is y. Okay. That doesn't look very good. So let's see. It doesn't really remove it. I'll erase it. And oops, part of the table got erased. Okay. So we'll do kind of next to the table. Alright, so y here. So the area A is equal to x times y. Alright, so let's give some dimensions. I have a table. I'll just quickly measure it to see how much I can measure. I actually don't have a long enough ruler, so I'm actually effectively adding the lengths, but let's not worry about that. So I got 90 already, and oh, okay, this is actually about 100 centimeters. That's it's from IKEA. They probably use SI units anyway. So here we have a 30, 60. Okay, yeah, okay, 100 by 60. So I'll make up some accuracies here. So let's just say x is equal to 100.3, and y is equal to 60.2. Okay, so these are in centimeters. So we're calculating area. Area A is equal to x times y. So 100.3 times 60.2. So you can pause here, use a calculator if you want, but it's pretty close to what is this? 60. Let's see, 6,000, right? Close enough to 6,000. Okay, I just got my Python calculator. So 100.3 times 60.2. Okay, we have about 6,000. Okay, 6038.06. Okay, 6038 bring that back again. 06. Okay. 06. So altogether I have 6 digits. So how many digits am I supposed to keep? Well, here we're going for overall sig figs. So this number x has 1, 2, 3, 4. So 4 total sig figs. And we're going for a total again. So 3 sig figs total. Okay, so again we're doing a minimum between the total sig figs of the two numbers, and that should give a 3. So what this means is with less basically with less sig figs, you're multiplying into a number with more sig figs. You're reducing the significant figures of the more sig fig numbers. Okay, so now we're only able to keep 3. Okay, so what is this number though? 1, 2, 3, 4. Oh, okay. I'm going to round at the ones place. Okay, I'm actually tens place. So round it up, right? 8. So 6 0 4 0. But this is ambiguous. Do I have the 0 as significant or not? Right. So let's say this is centimeter squared first. In order to make the ambiguity go away, we use scientific notation. So 3 digits, right? 6.04. So moving that decimal point place from behind the 0 to behind the 6, I need to do 3 separate moves. So times 10 to the third power, and that's 2 centimeters squared. So 1, 2, 3. So this is, and let's move that up a little. So this is 3 sig figs, and this 3 or 4, right? So you don't know. Whenever you get into this situation where there are trailing zeros that are not all significant, you have to use a scientific notation in order to express the number of decimal places that are significant, right? So that is that's multiplication. And division does the same thing, except that this is just divide, and you're going for the minimum amount of total sig figs. And addition, again, basically a minimal amount of sig figs after the decimal places. This actually gives you an interesting thing. If you add a very large number with a very small number, and that small number may not even be added in that number at all, such as this. So let's do something like say if you there's a joke basically about museums. Say if there's a dinosaur bone or a fossil that say one museum curator, when the curator started, the more senior person told the curator that this dinosaur bone is 6 million years old. And well, that has its significant figures. I don't know how many, but it cannot be as accurate as years or even days. And then when the young curator become old enough, and they'll say, oh yeah, this bone is 6 million plus 30 years old, because this curator has worked there for 30 years. But is that 30 years significant to how many years the dinosaur bone is not, right? So let's do that. Let's have a number. This is the example of using addition. So let's have 6 million years, 6.00. Let's say that we're able to determine down to thousands of years. Okay, millions. This is 100,000, 10,000s of years of an accuracy with our say carbon dating. So times 10 to 6 years. So this is 6 million years. And we add about 30 years of the whole career of a museum curator. So we're saying that this one's going to line up with that one's decimal places. Okay, so let's do that. 6 0 0 0 0 0 0. See, that's the decimal place, right? And then 30 is here. 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 So this number has no significance after that, and actually its significant figure ends here. This is the last sig fig. So our result 6000030 here, we can only carry as accurate as the least accurate ones. Although it's not really a decimal place, we can do that, and we'll still end up with 6000000. Another way to express this is to shift some decimal places around and write the 6 million into maybe 6,000. So 6,000 dot, well, there's no sig figures. Actually, let's not write 6,000. Let's write 600. Okay, 600. And this is actually going to be times 10 to the, how many zeros did we lose? 1, 2, 3, 4. So, okay. And then there's no significant figures after decimal places. So effectively we have a zero after decimal places. So how do we write 30 in these terms? So we divide 30 by 10,000. So it's going to be okay, so 1, 2, 3, 4. So 2 zeros, 30. Right, so we'll get 600. This is also times 10 to the fourth. 0.0030 times 10 to the fourth power. So as we see, 600 doesn't have any sig figs after its decimal, so we should cut it off. There's a 0 sig fig after the decimal, so right here there's nothing, right? 0 sig figs. And this one has basically all these. So now we know that we should keep 0 sig figs, so we should get 600. Then there's still 10 to the fourth power. So we still end up with 6 million. Or 6.00 million. Alright, thanks.